Welcome to RISE Learning Machine Seminars. I am Olof Mogren. I'm a machine learning researcher here at RISE. RISE is Sweden's public research institute, and this is our open weekly seminar on AI and machine learning. This particular seminar is organized in collaboration with Climate AI Nordics, a network of researchers in the Nordics working on AI to fight climate change. This meeting will be recorded. Let us know afterwards if you want to be removed from this recording. Otherwise, it will end up together with a collection of many great talks that we have already on our YouTube channel, which you can check out after this one. Today, I have the luxury to introduce Peter Dueben, who is head of Earth System Modeling at the European Centre for Medium Range Weather Forecasts, ECMWF. He's been at this position since 3 years back, and he's also an honorary professor at the University of Cologne. He defended his PhD at Max Planck Institute for Meteorology, and he then did a postdoc with Tim Palmer at the University of Oxford. He has also been working as the AI and machine learning coordinator at ECMWF before his current position, and he's been a university research fellow of the Royal Society, working on machine learning, HPC, and reduced numerical precision in weather and climate simulations. The topic today is the digital revolution of Earth surface system modeling. And with this said, I will stop my screen sharing and hand over the word to you, Peter.
Thank you very much. I'll also start my sharing. You should see the slides now, I guess.
Perfect. Yes.
Yeah. So I'm going to talk about the digital revolution of weather and climate predictions or Earth system modeling. And basically, I'm going to talk actually about three different revolutions. But before doing that, I just wanted to give you like a one-slide introduction about the ECMWF, the European Centre for Medium Range Weather Forecast, just to kind of know where I'm coming from. So we are a research institute, but we also provide operational weather predictions. So we literally run operational forecasts with a global model, and then we provide those weather predictions for a couple of days into the future or all the way until monthly and seasonal forecasts. And we provide them to our member states. So you can see the blue countries on the right here are our member states, so that they can basically use this information of global weather predictions. And since we have our own operational forecasts, we obviously also have supercomputers actually. So we are also a supercomputing center. And we also build kind of global Earth system models ourselves. So we have a physical model, the integrated forecast system or IFS, and we have an artificial intelligence model, which is called the AIFS. So just in general, we are not only research, we really also like an operational prediction center. So what is Earth system modeling and how do we actually model the weather and climate? It's kind of quite a tricky task to, in principle, do that because of several reasons. If you look into the Earth system, you will basically, first and foremost, see that this is a very large system. So you have basically a lot of space to cover, and that means basically that you have always only limited resolution in your system. You have also a very complex system with a lot of different, components interacting with each other, like atmosphere, ocean, atmosphere chemistry, land surface, sea ice, land ice, and all these kind of things are interacting. So you also need kind of fairly complex systems. And then also it's a chaotic system. So you have basically turbulent motion in the fluids like atmosphere and ocean. So therefore, basically you have exponential increase in errors and at some point you will get problems. So it's building like a perfect prediction systems 20 days into the future is basically impossible. And then the question is like, how far can you get? So it's a difficult problem, but we actually managed fairly well to kind of increase our ability to kind of simulate both the Earth system in principle on weather and climate timescales. So what you see here is actually how the forecast accuracy went up over the years. So on the x-axis here, you have the time in years over the last couple of decades. And the different colors here basically are showing you the forecast quality for different lead times. So you have 3 days in blue, 5 days in red, 7 days in green, and 10 days in yellow. And what you should see is basically that those lines are all going up over time. So we basically have a steady improvement of weather predictions over time. And that means that we're kind of getting better and better. And that's due to our models becoming better, our physical models, that's due to kind of our use of data and observations is becoming better, but also really because high performance computing is becoming stronger, and therefore we have more compute power and we have higher resolution. So that's what often people quote as a quiet revolution of numerical weather predictions, that basically our numerical weather forecasts kind of increased over time and became better and better. That's the first revolution I'm going to talk about. The second one is now the digital revolution. And here I brought you another plot where you have basically compute time against time and compute power against time. So again, on the x-axis, you basically have the years in decades, and the different boxes here are the different supercomputers that we worked with at ESNWFs. And the height of the box basically gives you the sustained performance that we achieved with our models on the different supercomputers. And you can see that it's basically like a linear increase in compute power over time in the plot, which is logarithmic. So you basically have an exponential increase. And that's what people often say is Moore's law, as an exponential increase of compute power over time. And that basically allowed us to increase the resolution of our models systematically over time. So the red line here is basically the resolution of our weather forecast system. It starts with 200 kilometers or 210 kilometers. And nowadays we kind of work with 9-kilometer global resolution in our systems. The problem is now that if I'm looking into kind of the expected increase in compute power for our next machine, it actually looks not very nice, in a sense that the cost for hardware is really exploding in recent years, and it's unlikely that this kind of linear increase here is going to continue. So we're kind of seeing now really the end of Moore's law in that sense. We can't really just wait for a couple of years, get a faster supercomputer and get higher resolution. We actually have to kind of really think about how to get more performance out of hardware that we have right now. And this is in particular a problem because the 9 kilometers here is kind of basically it's kind of very much accepted that if you kind of could go from 9 kilometers to 1 kilometer, you can actually increase realism of our Earth systems quite a lot. Because if you go to 1 kilometer scale simulations, in principle, you are able to resolve like explicit, like deep convection in the tropics, for example, that are very important for the energy transport in the atmosphere. And you would also be able to resolve more of the topography and mountain ranges and stuff like this, which also would really increase your solution quality. So we really want to get down with this number further. And then if you don't really expect a change in peak performance and you still want to get more performance, you basically have to look into the sustained performance. So how much you can actually get out of a specific hardware with a specific peak performance for your application. And we've seen this already a couple of years ago. In 2015, we wrote a paper about what we called the digital revolution. So the idea that you really want to kind of revise your physical models in a way that you can really make use out of those very large supercomputers, like exascale compute power, basically. And to do this, you basically need to change those huge models with 1 million lines of code into something that is kind of more manageable. You need domain-specific languages, you need portability, you need machine learning, and all these kind of things. And then you basically hope that you can revise your forecast system in a way that you can make use of those machines. And this was actually kind of quite successful, in particular in Europe, because we had a very large program, Destination Earth, that was funded by the European Union and that basically allowed us to kind of really revise our model systems and make them more usable on the state-of-the-art supercomputers. And here we develop what we call digital twins. And I've shown you this plot before, but I haven't really told you that on the left side here you have a simulation, and on the right side you have actually observations. So we really are at a stage of quality where you can really distinguish a lot, like the observations from the model simulations in terms of the quality. And this is what we call a digital twin in our sense. And this also means that you can now basically use those Earth system models as a digital laboratory and kind of play around with different things, like, I don't know, getting rid of the Amazon rainforest, for example, and see what's happening to the Earth system. So Destination Earth was quite successful. There was a lot of work going on to kind of port these models to Euro HPC machines in particular, so the largest public supercomputers we have in Europe. And we have been successful in a way that we can now run at least 3 model configurations globally with kilometer scales or a couple of kilometer resolution. And we kind of are able to do this with throughput rates of like 100 simulated years per day, for example, which means that you can actually run like very proper numerical weather forecast type simulation or also climate type simulations for several decades. And this video is just to outline like what these models can do and to some extent also how amazing they are. So all the fields that you see here are basically part of our model simulation. So we have really global models that run and really get the interactions right between topography and cloud fields and so on. You get like very realistic cloud fields in principle. You can compare them against observations. They look very similar. You can really understand processes better by looking into the three-dimensional atmosphere and so on and so forth. So I think this is quite an achievement for European science, really, that we are able to kind of build those very high resolution models and really can look into the physical fields in detail beyond of what we can just observe, basically. So that's all good news. So kilometer scale models are basically doable and useful in Europe already. But that's not the reason why you are listening to this talk. I guess the main reason you're listening to this talk is really machine learning. So let's come to machine learning then. That's obviously the third revolution that I'm going to talk about, the machine learning revolution. And what I brought you here is actually a video of, on the left side, a physical model, the IFS at very high resolution. And on the right side, we have a video of the AIFS, the machine learning forecast, basically. And the first reaction should be, okay, this is a bit disappointing. The machine learning forecast looks much coarser and kind of has a 6-hour time step instead of like a couple of 100 seconds, for example. So obviously, if you were picking one of those two options here, you'd probably pick the physical model. However, it turns out that actually, even though the machine learning model has not so much detail in that sense, and actually the solution quality in terms of the forecast scores is actually better for the machine learning model than in the physical model. So there's kind of quite a different thing now. So there's this new kid on the block with machine learning. It's different to the physical model. It's often better, but we have to understand a little bit more like where this is coming from and how this is going. It's a bit of an unfair comparison because by now we actually use generative machine learning as well for the right side, so that you will have more small-scale structures as well, and the resolution is also increasing. But just to get this notion that actually we have a fairly different beast here if you kind of simulate something with machine learning model or with a physical model. But the machine learning model is very successful. So the plot on the left side here is has been very scary for me at the time. So what you see is it's basically what we call a scorecard. So on the x-axis here, you have again forecast lead time in days. So from 1 to 10 days and forecast lead time from left to right. And on the y-axis, you have all sorts of different physical quantities like velocity, temperature, geopotential height, and so on at different vertical levels, for example, 1000 hectopascal or 250 hectopascal, and so on and so forth. So each of those boxes is basically a specific score for a specific forecast, for a specific quantity, for a specific lead time. A lot of detail in this plot. Don't think about every single box there, but just to say, whenever this figure is blue, this basically means that the forecast that Google was doing with their machine learning model in 2022 was better than the physical model forecast that we were performing at ECNWF. And that's quite a statement, right? ECNWF is an institute that developed basically physical models since like 4 or 5 decades. And now Google is coming along and building a machine learning tool, and suddenly they get better forecast scores. So that's kind of quite scary in principle. And it's also kind of quite clear that machine learning will make a big difference in principle on Earth system modeling. And so machine learning, just think about supervised learning as inputs to outputs, and you learn the mapping. Again, kind of coming back to the difficulty we have in Earth system modeling, you have a complex system, very nonlinear, a lot of interactions between components you don't know. And also you have a lot of data. So ECNWF has an exabyte of data of weather and climate primary data, basically. So both from observations and models. So you have a very complex system that kind of is really a challenge for numerical methods. And then you have a lot of data, and it's clear that if you have this mapping procedure that is very efficient, extract information from large data sets, that this is useful in many different ways in Earth system sciences, basically. And also, we have a specific data set that's called ERA5, which is what we call a reanalysis. And what's happening there is basically we run our model for the last 40 years, and we constantly feed in information from observations into the model. So we basically kind of always push the model towards the observations for the last really decades, basically. And doing this, you use a physical model and the physical data simulation system, but then you end up with a time. The timeline of how the atmosphere evolved over the last 40 years, basically. And you have a very nice open data set freely available on the web, and it's kind of dense and kind of high quality in principle. And that's a data set that can really be used a lot for machine learning methods by basically just going going along this trajectory of era 5 snapshots basically, and then learning how to update one field to the next from 1 hour to the next, for example, and then you end up with a fairly good forecast system in principle. So there's a lot of data that can be used. And if you then basically think about your machine learning structure, you would normally want to have some sort of encoding decoding structure. But there are different ways how to do this. There's the Google approach with kind of multi-grids. You can use graph neural networks, basically. You can use Fourier neural operators and on the sphere and stuff like this. So there are plenty of different ways how to actually train a machine learning model. But in principle, it's not that difficult because you have a lot of data at your fingertips, basically. So coming back to Google, this was a situation of 2022, actually on Christmas, where they showed that they can basically beat physical models with their machine learning models. So the question was obviously that the community asked itself, like, how do these models actually work? And it turns out that there were kind of good reasons why we should be skeptical as a community in principle when using those machine learning models. And first and foremost, the most important one is actually that these machine learning models tend to smear out. So what's happening is if you have a trajectory of the atmosphere going from top to bottom here at the truth, you see that obviously the atmosphere is evolving, but the gradient, the sharpness of the gradient is staying the same basically over time, from 0 hours to 72 hours. Whereas for the machine learning model, you basically smear out structure. So you see that you're kind of losing detail as you go ahead. And this is kind of quite clear. It's a deterministic model. It's trained with root mean square errors. So you would expect double penalty effects basically. And it's kind of quite given by the loss function that you're using that these models are smearing out. So domain scientists were asking a lot of questions like, are these models actually useful? Are they not just kind of interpolators that provide you like a smeared out solution that is not really useful for users anymore? What about extreme events and so on and so forth? And we used the time basically from 2023 until now to really make a very detailed analysis. So we started in 2023 and published a paper in summer there where we basically had the first data-driven forecast that we looked into and looked for extreme events. And it turns out actually the machine learning models are very competitive in the sense that they are physically reasonable and also for a lot of extreme events actually providing better results than the physical models. We also pushed those machine learning models onto the web page. So we basically kind of published results from the Google model, for example, and the NVIDIA model to kind of get the domain involved as well and to kind of really look into specific forecast situations and get feedback from the community. And again, we didn't really receive negative feedback in the sense we rather actually received a lot of positive feedback that the models are useful. And then we also kind of started to build our own model. And now we basically have the AIFS, so the Artificial Intelligence Forecast System, that is also like a global prediction system that is now running also operationally for deterministic predictions and is also competitive with Google results. So for a domain that normally thinks in 5 years timescales in developments and where a physical model development normally takes at least 15 years, this is quite amazing that we actually were able to within a year basically kind of catch up and build our own forecast system. So this is really a revolution in that sense that kind of nowadays the development scales are really very different to what we're used to. So coming back to those questions, they are very, I mean, in 2023, these questions were very valid in the sense like, can we actually use those models? So the questions were, for example, can we avoid the smearing out of the forecast structures? And also, can we learn model uncertainty? So in weather predictions, it's not only important to predict the temperature, for example, in 5 days from now, but it's also important to get uncertainty values for those predictions. And again, Google was actually faster than we were in a sense that in 2023, now again in Christmas, they published a paper where they used diffusion methods. And by using diffusion methods, they basically use generative training, and then you can you can keep the sharp gradients basically. And they also show again that they are very competitive and basically produce better scores with the machine learned models for ensemble simulations where you represent uncertainties when compared to the physical model. And again, we basically follow the trend, and we also basically kind of pushed AIFS to kind of be trained on ensemble simulations using either diffusion methods or also score-based simulation basically, and we also kind of find that our scorecard is now nice and blue in the sense that the machine learning model is better than the physical model. Olaf, you have a question?
Yes. Have you evaluated sort of what kind of errors are being done? Do you get the same kind of errors from the machine learning model that you get from the traditional model?
That is a very good question. So often, yes. So often when the physical model is bad, then the machine learning model is also bad. And often when they also seem to be bad for similar reasons, but not always. So there are some cases, actually, I think that's maybe the next slide.
Okay.
Yes, it is. So this is, for example, one just one forecast basically where there was a very strong forecast error in the physical models. So top left, top right, and bottom left are all physical models. And you see basically a very strong forecast error over the US that was triggered by the interactions of the jet stream with the Rocky Mountains. Well, a lot of domain-specific detail, but basically we know kind of where the error was coming from. But in the AIFS system, so the machine learning model on the right, you basically see that this system actually avoids this very strong error pattern. So there are differences, but overall, actually, you often see also similarities between the model. But I think what's even more important is that we don't see any forecast busts in AIFS in a sense that they would be more significant than the physical model. So if you just build a machine learning model and you run it, and you wouldn't know whether you can trust it, for example, for extreme events. So if you have an event, for example, happening over Stockholm, where you have basically like a precipitation pattern that would only happen every 100 years, but you only had a 40 years training data set, you may not really actually be able to represent that correctly. But it turns out that AIFS and other machine learning models, that they are actually more robust to these events that you may think. So in those, ever since we were running those machine learning models at ISNWF, we've never seen like a horribly gone wrong forecast with AIFS or the machine learning model. So it's kind of really something that developed a lot of trust over time. And therefore, the two questions here, can machine learning models represent extreme events? And can they learn physical consistency? Basically, yes, in a sense that we don't really see any kind of frauds in those models. Next question is, can machine learning do data simulation? So what we have is basically that we collect observations every day. So something like 800 million observations are coming into ISNWF every day. Then we perform data simulation where we bring in kind of the last model state basically together with observations and we optimize. And via data simulation, we generate initial conditions and then we run the numerical weather forecast model into the future. And then we do post-processing and product generation as kind of a bit of an afterthought basically after the model. But the question is, can we actually use machine learning for this step of data simulation? Because if we cannot, we would still need a physical model to generate training data like error 5. If we can, we may actually get rid of the physical model altogether, because then you can basically just use a machine learning model end to end from observations all the way to the prediction. And there are good reasons why this should not work. So there's basically not a training data set that is very good, like the error 5 data set, for example, for the forecast model. So it's much more work actually to bring all these kind of data sets together for observations to build a good training data set for your data simulation. Then also, the further you go back in time, the more observations you will be missing. So the more the number of observations will go down, and this means that you actually have a very limited time horizon where you have a lot of observations. And also, the further you go back in time, the larger will be the null space, where you basically haven't any information like how to fill in state variables, basically, because they're not observed. And another question is also what's happening if a satellite, for example, appears or disappears. Those satellites can live for like, some of them live only 3 years. If you need like 1 year of training data to actually be able to use a satellite in the first place, then this is not going to help you very much in the lifetime of a satellite, basically. But there are also kind of reasons why it would work. One of them is that all the individual steps of data simulation, like observation processing and kind of minimization of cost functions and so on and so forth, we know that we can do with data simulation. And we also know from the ensemble systems and the Google papers, basically, that with diffusion methods, for example, you can really do a lot of nice gap filling in principle. So it's also kind of quite possible to think that you can fill in a lot of gaps where you have a lot of null spaces. And also, machine learning is quite amazing. So we have seen a lot of kind of amazing results in the past where we didn't really expect it to work, and it did. So why not here? And we have a study where we basically go quite all in the sense that we actually kind of take only information from observations, and we just try to predict observations, and we call this AI DOP. And we basically kind of get quite good results. So this is the latest, greatest from Mihai, who's working on this. And what you see is basically forecast errors that are increasing over time. So the x-axis is time in forecast days from 0 to 10. And you have three models now. The green one is the AIFS, that is kind of the machine learned forecast system. The blue one is a physical model. And the pink one is now the one that is doing data simulation with just purely with machine learning. So this hasn't seen any information from a model, from a physical model at all, whereas the green line has basically seen information in the training data set. And what you see is basically AI DOP is not quite there yet, in a sense that the results are clearly worse than the AIFS or IFS results for many of the quantities. But it's getting there. It's really getting interesting, and this is really kind of a cutting edge research area. So I would say it's almost that machine learning can replace data assimilation. It's also interesting if you think about how the machine learning models can now actually help you to understand a bit better how predictability works and how the models are working. So there are some general assumptions about the predictability of weather. You probably all have heard about this famous butterfly effect. So the idea here is that you have errors in the small scales and the initial conditions, and then you run a forecast, and errors will grow exponentially in time, and they will also grow in the scales that kind of go from small scales to larger scales, and so on and so forth. And at some point, you will basically destroy your predictability. And also, as you turn this around, if you kind of increase resolution of your model by a factor of 2, you will basically get more and more scales resolved. But the problem is that the smaller the scales, the shorter they lived. And that basically means that the smaller the scales, the less you will gain in terms of predictability and the forecast horizon. So that's kind of the common knowledge about how this butterfly effect is working and how you can basically limit predictability in weather. However, with the machine learned forecast, we see there's a nice paper by Vonech and Hakim, and they basically demonstrate that you can deterministic forecast skill all the way up to 30 days by basically optimizing initial conditions through a machine learning model, by using the property of a machine learning model to be differentiable. And this is kind of quite interesting because it somehow contradicts this idea of having predictability limitations from the butterfly effect. And in particular, this is the case because they show that if they optimize initial conditions, they actually can optimize initial conditions on the large scale rather than the small scale and still get this benefit. So to some extent, this means that kind of the butterflies are not to blame here in a sense, and you basically get maybe another perspective as well on like how predictability in the atmosphere is actually working for weather and climate scales. So a lot of interesting science. Another part where a lot of progress is made or a lot of studies are done is basically what we call hybrid model. So if you have a world where you have a 100% physics-based model, like we had before machine learning entered the stage, and you have the world where you have a 100% machine learned model, there are also a lot of different grayscale applications in between. So there are a lot of ways of how to combine physical modeling and machine learning model. And I think that's really also very interesting to look into, and also a field strongly developing at the time. And I'll just give you two examples. One of them is an approach that is called nudging. So basically, the normal idea was that if you kind of build a model and you kind of basically increase resolution, you will get kind of better and better predictions. And as you kind of increase resolution, you will get the large scale features of the system better and better resolved, and therefore you get basically kind of push your limits in predictability in principle. However, machine learning models actually turned out to be fairly coarse. So I've shown you the result of the smearing out structures on the GraphCast paper. And it's kind of clear that those machine learning models are working well on the large scales, but they're kind of clearly missing energy in the small scale. So this is kind of a spectrum here, and you see that the machine learning model is actually kind of really going down for the small scale features in terms of the energy that is in those scales. So the machine learning model is working well on the large scales, but not so much on the small scales. And there's been a study by the Canadian Met Service where they basically nudged the physical model to the machine learning model for the large scales only, and they get very nice results. So by doing this, you're basically forcing your physical model with the machine learning model. You get better forecast scores for the physical model, but you also get more physical realism and also higher resolution in principle for the small scales because the physical model is getting those very, very nicely right. So it's kind of a nice way of actually kind of forcing the physical model towards the machine learning model, is that you combine the best of both worlds. So you would basically get the better forecast scores, better tropical cyclone tracks, but actually more realism, for example, for the representation of the tropical cyclone on the small scales. This is one example. Another example is actually the other way around. So the other example is actually trying to represent the physical processes that are normally happening at the grid scale with machine learning. And there's a study by, again, by a Google team, where they basically took a dynamical core, like a physical model for the fluid dynamical equations, and they used machine learning to actually represent the small scale features, the physical parameterization schemes. And again, they get very good results in principle. In particular, they get very stable results for long-term simulations. And the reason why I showed you those two studies is basically because both of those studies are kind of really giving you the best of both worlds in a sense. So but both of those studies are very different. So the Canadian approach basically kind of used the large scale systems from the machine learning model and the small scale systems from the physical model. And this approach here by Google is basically using the large scale, the physical model, and the small scale, the machine learning model. So basically, it's really up in the air what's going to be the silver bullet in the future. So we have a lot of different approaches and a lot of things to explore here. Another thing is climate simulations. So you don't only want to get the weather right, you also want to get the climate right in Earth system modeling. And here it's actually kind of quite, well, different. You get different answers how much is going to be possible if you ask domain scientists and machine learning scientists. So why would it not be possible to use machine learning in climate? So if you do climate simulations, you push your climate state obviously into a warmer world with anthropogenic forecasts, forcings in CO2 and so on. So basically you're changing the distributions of your fields from the data that you have for training for nowadays climbing into the future where you have a warmer world. So you basically have to extrapolate into a new climate state. And we know from machine learning that that's difficult in nature. We also don't really know how to represent CO2, for example. So all the models that we have developed for weather, they don't even know CO2. They just realize that it's getting warmer over time, but they don't really have a value for CO2. If you want to do climate simulations, you also need more complexity. So just the atmosphere is not enough anymore. You also need ocean, sea ice, land, aerosols, and so on. And for the deep ocean in particular, the timescales that you have are like on decades of the variability. However, you only have decades of data to train from. So you basically know that you're not going to have enough data to learn the deep ocean. And then there's also like another fundamental problem. If you want to build a climate model, it's probably doable. You can build one and then you can run it to 200 and 2100 the year, but you never know whether you can actually trust the model or not. So kind of actually trusting the model is much more difficult if it's not physics based, but actually machine learning based. So it's a fundamental problem there as well that you, even if you have a model working, you still need to be kind of trustworthy basically. Why would it work? Because we know that we can run those machine learning models already for decades for the atmosphere forced by the ocean. We know that we can learn the different model components. We also have extreme problems with the deep ocean in physical models. So it's not that you basically just lose something that you cannot do anymore, but you actually also for physical models, the deep ocean is a very difficult task. The machine learning models for weather are remarkably robust for unseen weather situations. So we can probably put some trust in there. And I think the most important point for me is also there will be people working with machine learning and climate modeling. So there will be machine learned climate models, and those machine learned climate models will perform extremely well in nowadays climate. So it will be very difficult to argue against them actually for future climate as well. So there's going to be a bit of a problem there in the sense that there will be machine learning scientists who claim that these models are very nice, and then domain scientists who claim that these models are not working at all, and probably both are right in some in some kind of aspects, basically, of the question. And I'll skip this one. But to show this, actually, there's a nice study by Thomas Rakoff and others, where they actually looked into those weather models and they applied it to the weather of the future. So what they've done is they've taken three different trajectories. One of this was from 2023, and one of them is from 1955, and one of them is from a future climate in 2049 from a physical model simulation. So basically, the model was trained on the climate of the trajectory in the middle, but it was applied to past climate that was colder and future climate that was warmer than the training data. And what you see is basically a lot of small hairy features here. So a lot of a lot of lines in the plot that follow the big trajectories. And those lines are actually forecasts from the weather forecast models that were machine learned models basically. And they were run basically a couple of weeks into the future from each given state. And what you see is that there are trends. So for example, for the warm climate trajectory here, you see that all the lines are going down. And that's a clear indication, basically, that the machine learning models are kind of pushing back towards their own attractor. They're leaving the warm weather, basically, of the future and kind of want to go to the colder state of 2023. That's a clear indication, basically, that these models fail to represent the climate state there. So they're not really used to this climate, and they just want to go back towards their attractor. So this means that these models are not yet ready to work on the future climate to some extent. On the other hand, actually, the individual lines here look very reasonable if you look into the details, and also the forecast scores for weather are actually quite good. So you can argue that these models are not able to kind of be used as climate models yet, but they are already able to kind of look into climates like extreme weather scenarios, for example, of the future. So it really depends a little bit on what question you want to answer, whether your model will already be ready or not for different application areas in climate. So the question is like, how will physical modeling develop and how will machine learning modeling develop in the future? For the physics-based model, it's clear that development efforts will to some extent reduce. So, I mean, a lot of people are working on physical models, and we will probably have machine learning models coming in that will replace those physical models in a lot of application areas. So naturally, the physical model is kind of going to reduce in effort. They will still be needed. They will certainly be needed for data set generation, I'm pretty sure. And also they will be needed for things like gray swan events, like events that you have never seen before. If, for example, a volcano in Sicily would just go off next week, the machine learning models wouldn't even know what this is, right? And so it could not possibly represent what's happening there. Also, tipping points in climate, I'm very sure that machine learning models will not be able to rip them correctly. On the other hand, they will basically need less focus on the forecast scores because their machine learning models are better. So they can probably kind of be more focused on realism. And then the kilometer scale model simulations from the digital revolution are really kind of the way to go with modeling, that you have the best possible high resolution model in principle. And to be successful in the future, they also kind of need to have more effort to be portable and usable, in a sense that a machine learning scientist nowadays can publish a paper on a source code with 10,000 lines of Python code, whereas the physical model needs a million Fortran lines, and that's not sustainable anymore. So I think we will have to kind of revise those models to make them more usable. Then for machine learning models, efforts will increase. There will also be many different application areas and how they interact. And the question is like, how many different models will we have? And I'll come back to this in a minute. There will be more data sets and models that will increase in size, but we don't really know yet what the limits are. And for the modeling centers, we really have to revise the physical models. We have to embrace machine learning, embrace federated computing and federated data, invest in good visualization, and also maybe make a difference between operational HPC systems and scalable HPC systems, where you basically scale the largest model for training, but not necessarily at the quality of the HPC center that can also be used for operations. And in Europe, and generally, we are very well placed here. So with initiatives like Destination Earth, we actually have all we need at our hands to kind of really be world leading in this field. So it's also good to see, I think. So how many models do we need? There's an approach to what we call foundation models in a lot of different areas. So models that are basically developed for not just one application areas, but many of them. And we have now just kicked off a project in February that is called the Weather Generator, where we want to build one of those foundation models as well for the weather and climate domain. So we want to build basically one big model that can be applied to a lot of different application areas. Why is this useful? If you want to build one model that is kind of similar to a foundation model, as we know it from large language models, basically, we know that we will need a lot of compute power. So this is kind of just a plot showing you over time on the x-axis how the size of large language models and foundation models and languages basically increased over time, again exponentially basically. And The AIFS, so the biggest model that we're training right now is somewhere here. So this is 2025, and it's around 200 million degrees of freedoms. So it's far away from the scale of size of those large language models, for example. And Weather Generator is basically trying to kind of push those limits much higher up so that we can basically train models with billions of degrees of freedoms, and then we'll find out how good those models will be in comparison. We should have enough data for this. And then the other thing of a foundation model is that it's normally multimodal, so you use a lot of different data sets for training. And in our case, this means that you're not only using reanalysis data, so the forecast models that we're using today are basically all using the same data set, but you're actually also kind of putting in a lot of simulated data from high resolution simulations and also observations. And then you basically take whatever data you have available at a specific location and point in time, and then you can use that data to kind of predict fields, and those fields should be able to kind of be workable for the 22 application areas that I showed you before. And the challenge here is now that we basically want to build tools that can run on the globe with 100-kilometer resolution, but also at a limited area where you only have like 100-meter resolution, for example. So you kind of need to breach a lot of different physical scales in both space and time to kind of make these tools useful. I think I'll skip over a couple of details here. And yes, this is my last slide. So basically, I showed you three different revolutions. The quiet revolution, where you basically have the constant improvements of weather forecasts over time, over the last couple of decades. That's kind of finished now. Then we have the digital revolution, where we basically have now pushed the models to kilometer scale simulations, and we see a lot of benefit and really cool like data sets that we also generate. But the machine learning revolution catched up in the meantime, basically building models that are producing better weather forecast in a lot of aspects when compared to the physical systems. And we're still exploring the space, like how we actually kind of make the best machine learning forecasts and how we combine them as well with physical models. And then I think the good news is that for the next steps, these models will still become better. So it's kind of quite likely that the weather forecasts for you will also still become better with machine learning, but also with initiatives like Weather Generator, where we build like foundation models as well for weather forecasts that then basically scale the size of those forecast systems from 100 million to tens of billions degrees of freedoms. Okay, thanks a lot.
Thank you, Peter. So while everybody thinks of their questions for Peter, I think I will start to ask one question. Um, so I'm thinking of you have mentioned Google and NVIDIA here with the GraphCast model, for example, and GenCast and so on. How are they interacting with you, or how are you interacting with them, if there is any such interaction? I know that you took the GraphCast model and you sort of put it on your website. Do you get any details of what they're doing in their modeling? And how is this working?
It's a very good question. I don't really know the answer, to be honest. I mean, because when Google started to go into this domain, they were extremely open, and they actually really asked for a lot of feedback as well, in the sense that they really wanted to build a good model, and they realized early that if they want to build a good model, they actually need to get the feedback from the domain scientists as well. So they were very interactive and really asked a lot of very good questions. They're smart people there. And we answered them and we helped them, and it was kind of great to see that they were also so successful with the models, right? So it was really good for the domain that the Googles and NVIDIAs and Huawei's and others basically built those models to kind of show us where to go, because the domain was a bit too conservative, I guess, in a sense that we never really believed in this kind of full-blown machine learning models replacing physical models at some point. We rather wanted to look into machine learning for like specific components of the physical model rather than the whole thing. So it was great that the technology giants basically looked into this and pushed the domain. It's a bit unclear what's happening now, in a sense that Google is, I think, now actually kind of looking into operational predictions as well, which is basically means that they're now stepping on our toes, in the sense that they actually also have forecast products. That's not, again, not necessarily a bad thing, and not necessarily a problem. But I'm not 100% sure. I know what Google will do in terms of the weather domain, for example, in the next 10 years. And the same is true for the other companies. So it's a mixed experience, basically. On the one side, it's great that they've done that, and I think we are competitive by now. So it's not that Google and the others are kind of miles ahead of us in a sense of forecast scores. So we also catched up nicely. But on the other hand, it's a bit scary to know that there are Google teams of 20 people looking into weather forecasts as well, because they also have different resources normally, like in terms of both human resources, but also compute resources and so on. So let's see where this is going. I don't know exactly.
Exciting and scary future then. Do we have a question from the audience? Sigrid.
Yeah, hello. Thank you. It was a really interesting talk. You had a plot earlier with the scorecard and you showed the different regions. So you had like Northern Hemisphere, Southern Hemisphere, tropics. It looked like AIFS was doing worse in the Southern Hemisphere. Could you comment on that?
I mean, generally, the forecast scores in the southern hemisphere are still better than the physical models normally. It depends a little bit on, um, I think the season as well that we're looking in. So I'm not quite sure which season the scorecard was from. But in general, I mean, the southern hemisphere is a bit different to the northern hemisphere as it's kind of less variable. We have less variability because you have basically more ocean to some extent and less mountain ranges, and also you have less observations to verify against. So there's also like more uncertainty, in particular in those scorecards where you kind of plot against observations. You have basically less points because there are literally less observations. So I don't think there's a general reason why AIFS should be worse in the southern hemisphere than in the northern hemisphere. I think it's more about how you verify it against observations and also the season that you have there.
Thanks.
Any more questions?
I guess I'll jump in with one. So kind of piggybacking on that, just to do with observations, how all these recent kind of ML models evaluate? Is it against observation data? Or is it against kind of reanalysis and simulation as well? And how is that kind of trade-off changing how you look at things like?
Yeah, very good question. I mean, this is kind of like one of the reasons why we were skeptical at the beginning, right? In a sense, like,
Mm,
oh yeah, you can get good results against the analysis, but this doesn't mean anything. And if you really want to kind of look into observations and so on and so forth. So let's phrase it this way, it's easy to be skeptical and easy to come up with a resolution. Yeah, I haven't really tested it properly and stuff like this. But actually, we've done that now. As a domain, we really have looked into all the different testings, and we have also the benefit in whether that we can test our models fairly well, right? You have huge amounts of observations, you have huge amount of data sets, you have then periods that you haven't used for training and so on and so forth. And it's really that these models are generally good. It's not that they're basically cheating by some statistical methods by looking training and probing against the same quantity of data and stuff like this. So these models are actually genuinely producing good results, and we have people at ESNLDF who are basically doing nothing else than looking into the physical consistency and observation and comparison and stuff like this. And it's not that there's a big problem with the machine learning models in principle.
okay. I guess maybe the problem with then going forwards was the climate long term
Exactly.
modeling.
Then
Yeah.
you basically you're losing the capability of comparing against the truth, and then things become much more complicated. Yeah.
Gabriele?
Yes, hi. Thank you. Very interesting talk as usual. My question is about you showed a lot about the global model because, of course, this is say more in your domain. But what do you think will be the future also for limited area models? I mean, do you think that they still let's say make sense? And since you're going for kilometer scale also with the global model and you have AI models,
Yeah.
of course, we know, I mean, we're part of one of the team that is trying to build AI-based limited area models. So do you see also limited area models going towards AI-based forecasts?
Yes. So a group of our member states are actually like many of our member states are actually looking into like limited area models for their specific area where they are like And they are producing very good results as well. So the structures of the machine learning models are not that different from the global one, but they basically kind of look into a limited area domain. Sometimes they couple it with like a global model, and then they kind of just zoom into the limited area domain. Or they also kind of just use a limited area domain and have a kind of the global model running and providing boundary conditions. And I think there's absolutely no reason why this wouldn't be successful and very useful. So we have seen very good results already, and I think this is also like something that is really growing right now. And I think for global modeling, we are now, well, 4 years into the developments. So we kind of started to converge to something basically. And for limited area model, there's still a lot of slope, and we see a lot of progress. I think the biggest problem to some extent is always what's the data set you're training from. So the more you go to finer scale, the more you will basically be limited in a sense that you don't really have a good reference data set. And so then the question comes in, like, what is the data that I'm training from? At the moment, most of the member states are using their physical limited area model and kind of train from that, and it's kind of good and well. But then the question is, how generalizable is this, and so on and so forth, and how many kind of different states do you have, and do you train from different countries and different kind of training data sets and so on. So long story short, it's a fantastic area to work in at the moment, and there's a lot of progress. People can do this, they can learn it. The question really is, what is the data set they're training from? And I don't think we actually know yet what the optimal training data set will look like. It could actually be a kilometer scale global simulation, why not? But it could also be that you have a general data set for global simulations, then you kind of refine on your local area model, for example. Everything is up there. I don't know exactly.
Thank you.
Will we be happy when we reach 1 kilometer resolution?
Well, we scientists are never happy, right? So we will find something else to work on, I'm pretty sure. But I think we've seen a little bit of a convergence there, and also so like the physical models. Since we know that the compute time is since we know that Moore's law is over, basically, I think it's unlikely that we will go yet after 1 kilometer to something else in the kilometer space. For the machine learning model, it's actually also interesting to see that the global forecast scores for like large scale features may actually not improve that much if you go to 1 kilometer. So the physical model actually kind of needs higher resolution, it seems, than the machine learning model. But then for the machine learning forecast, you would still want to get the local features right, because you want to get, for example, the wind in the valley right, or the thunderstorms or something like this. So I think it's kind of then more the question is switched. So you go from a problem where you want to have a better representation of the small scales to get the large scales right, into a questions where you want to have small scale data to get the small scale right. So I think the way of thinking will change there a little bit.
Interesting. Do we have one last question for Peter? I have one more question. Sort of you mentioned scenario modeling, and you mentioned sort of getting rid of Amazonas. Can you sort of elaborate a little bit on this? Is this something that you do, and in what kind of scenarios are you looking at, and who sort of who is sort of the who is asking for those sort of scenarios?
Yes. So I mean, in climate, it's kind of, in particular in climate, that's important basically. And you constantly ask the question, like, how is the climate state going to look like in, I don't know, 80 years from now or something like this. And to define this, you actually need scenarios. So for climate modeling, it's kind of quite usual that people produce different emission scenarios, for example. So they say, like, what happens if we keep emitting as much CO2 as we do right now, or even more or less? So you have kind of whatever you want to predict into the future, you already have a defined set of scenarios that you want to look into, basically. But these model systems that we have right now with the digital twins, they basically also really allow you to kind of look more into the details, and actually kind of to not just ask the question like what how warm is the Earth going to be in 80 years, but actually also kind of to be a bit more fine-grained. And then questions are coming up that are really also extremely important, like for example, how does precipitation change over Africa, or how hot will India become, or something like this, like very very fine scale, basically questions in the local area. And for this, it's kind of also really interesting to kind of then play games with the Earth system in principle, and those tools that we develop in Destination Earth would be able to do this. This is all physical. I don't know whether you could do it with a machine learning model, probably not, but with a physical model you can do that. And this is kind of the idea that you have in digital twins in general, right? That you basically have a digital representation, and then you can basically use it as a digital laboratory and kind of make tests. And we are at the stage where you can really do this quite successfully. And in Destination Earth, you could, in principle, also suggest scenarios that you would want to look into for a science project or so, and then we could run those simulations basically. So it should also be more interactive than it used to be in the past, in terms of the suggestions of different scenarios that you run.
Cool. So I think we will conclude this seminar. Thank you very much, Peter Dueben from ECMWF.
Thank you.
Next seminar is next week, May 22nd. We'll have John Martinsson, who is my colleague here at RISE. He will talk about efficient and precise annotation of local structures in data. So thank you all.